Our last section in Chapter 6 is called the trapezoid rule, and it gives us just one more way. We're kind of going back to approximating. We had moved from approximating the area under the curve using rectangles to learning then that if I put an infinite number of rectangles in there, that we could find the area under the curve using an integral. And now we're just finding another way of approximating, so kind of going backwards here to the more approximating idea. But using the shape of a trapezoid today instead of a rectangle. On our first example, it says let f of x equals x squared plus 3. Estimate the area under the curve on the interval from 0 to 4. It specifically says we're going to use 4 trapezoids this time. So to get us started, what we'll want to do is just give ourselves a picture of the curve from 0 to 4 so that we have something to work with. So if I look at the function f of x, start at 0, and I'm just going to plug in 0, 1, 2, 3, 4, give us some points to work with here. 0 squared is 0 plus 3 would be 3. Plug in 1 squared is 1 plus 3 would be up at 4. 2 squared is 4 plus 3 would be up at 7. Let's see, 3 squared is 9 plus 3 is 12. And the last point in our interval is 4 squared is 16 plus 3 is 19. So there's an approximate picture of our function on the interval from 0 to 4. And we're learning this new way of approximating area under our curve using trapezoids. And so what happens is, it is getting split into 4 equal ones, which is going to happen at each of our nice whole numbers here, 1, 2, 3, 4. So starting at from 0 to 1 would be where that one would go. And we go up to the points, and a trapezoid, all a trapezoid is going to do is just connect the end points, so the dots on our curve, the heights at each of those, okay, creating the 2 different lengths of your bases of your trapezoid. And then we would do the same thing for the next one, connecting those 2 points. Connect those 2 points. And connect those 2 points. And obviously, it's going to be a little bit different per function. But you can see on there, trapezoid approximation is pretty good. Better than our rectangles we're looking last time, isn't it? Pretty close. Okay. So then if we're using that to approximate the area under the curve, we would have to then find the area of each of those little trapezoids. So just again, a reminder on how we find the area of a trapezoid in this kind of a situation. So if we were looking at that guy right there, it'd be 1/2. The height is going to be the distance between those parallel lines. Well, if we had an interval of 4, and we have 4 trapezoids on there, each of our lines are going to be 1 apart. Calculator part first. Here's your non-calculator part. So the height of our trapezoid becomes 1. The bases then are the heights of each of those points along our curve, so 3 and 4. And we can do that for each of our trapezoids along here. Height's going to be the same, 1. The base lengths are 4 and 7. Next one. 7 and 12. And 12 and 19. Okay. Any questions on any of that? Good so far? Making sense? Just using a different shape to approximate the area under our curve. So if I were to actually total all of this up, let's see, that'd be 7/2 plus 11 halves plus 19 halves plus 31 halves. Somebody add that up for me there. $34? 68. Okay. Now, with that being said, because we have equal trapezoids, equally spaced across there, first of all, notice that every single one of them in our trapezoid formula used the 1/2, and they all had the same height, right? So as we talk about kind of things that they have in common, how can I put this in a slightly different way? But the other thing I want to point out is the base of this trapezoid right here was a base of that trapezoid right there. We see that base show up in there twice, right? And then this base right here, the 7, is the base for this one and this one right here, right? It shows up in there twice. And then the 12 also shows up here and here. And so what we get is that a couple of the bases, all the bases on the interior, show up in 2 different trapezoids. That and the common height and the common formula is the underlying explanation behind your trapezoid rule. And the trapezoid rule just kind of makes a faster way of doing that. Instead of drawing all the trapezoids and doing the individual area of each trapezoid and adding them all together, we can kind of collect it all into one thing. And it says this: our height divided by 2, which takes care of the first part of the area formula of the trapezoid, 1/2 times the height, height divided by 2. Because they all have the same height, then we'd only have to put it out there one time. It's like factoring out that GCF. And then what you see going on the inside of this is what I was just showing you, is that the 2 outside bases of our trapezoid were only used one time. So the first base will only show up in here once. The last base will only show up in there once. But all of the other bases of our trapezoids were used in 2 different trapezoids, in adjacent trapezoids. And so you see 2 times each of those values on the interior of that formula. Now, there is a formula for finding the height of your trapezoid. I don't know if it's worth memorizing or just understand what's going on. Is that this is the length of your interval divided by how many equal trapezoids we are drawing into that interval, right? It's not some magical formula I need to remember. How big is the interval? What are we dividing it into, right? That's the height of our trapezoid. This, also not worth memorizing, but it is interesting, is that your trapezoidal approximation, is the average of LRAM and RRAM. So trying to do this trapezoidal rule without a picture to look at and without finding the area of each individual trapezoid and adding them together is putting it into this formula up here. We can start with identifying the height of our trapezoids by looking at the interval that this one is happening on, which would be 2 minus 1. And they asked me for 4 trapezoids in that amount of time, so I would divide that by 4, which means the height of each of my trapezoids is 1/4. So a little uglier on that part of it. So putting that into our formula, it says take your height and divide that by 2, and I'll show it like that in our notes, but what is 1/4 divided by 2? 1/8. 1/8 times, and then the length of the bases come from plugging in at each one of these intervals into our function, right? Starting at our lower end of that interval. So I would start by plugging in 1. Well, 1 squared is 1. All I'm doing is plugging it into the function, right? Plus, and now we start multiplying each of these by 2, except for our very last one. But how far over? What am I plugging in next? 1.25. I'm moving over 1/4 each time, the height of my trapezoid, right? So the next number I would plug into our formula would be 1.25. Now, I would go ahead and just leave it like that and just type it all in at one time. Or you can go figure out what that is. but I'm just plugging it into my function. That is this too, is 1 squared, but 1 squared is 1. Plus, okay, let's move to our next one. I was at 1.25 here, so the next one's going to be at 1.5. Add another quarter or another fourth. And then we're at our last one. Your last one will always be evaluating at the last number in our interval, and that is at 2. 2 squared, plugging it into our function, or 4. Okay. Again, you guys are going to have to be on your calculators today because it's a lot of ugly numbers and a lot of typing today. So go ahead and type that in when I get a table that agrees. Yeah. It is. Depends on the function. Depends on the function. Yeah. All right, see a lot of inactive calculators today. Grab your calculators. Get working. Don't let your just classmates take care of it for you. 2.344. And you guys agreed? Perfect. Okay. Any questions for me on trapezoid rule? Now, I get to the test and it asks me to do the trapezoidal approximation and I panic and I can't remember this rule. Can I just go do the area of each of the trapezoids? Absolutely. This is just a faster, more efficient way. When we talk taking a timed AP exam and I am asked to do a trapezoidal approximation and I have to get things done quickly, that might help speed up if I know that formula. Okay. All right. So this should be, again, something you could not like memorize, but hopefully it'll make sense. Is it an over or an underestimate? When we were doing rectangles, it's really easy to see that if I were to like break this into 2 rectangles, or let's go 3 rectangles here, and I did for this particular curve an LRAM, which means I used my left-hand side to draw in my rectangles, I could see that I definitely got an overestimate because all of that was sticking outside of my curve, right? And if I did an RRAM instead, that it was going to be an underestimate because I had all of, well, we didn't even have that, all of this under our curve that wasn't taken into my estimate, right? Trapezoid is not as obvious, so I'm going to make it into 2 here. And when I'm connecting these dots, it's very subtle, so I'll try to draw it obviously here. Is that an over or an underestimate if it's concave down? Under. Close, but it's under. So then if we flip to concave up, and I connect those 2 points, you see how if I draw it a little excessively there, that it would be an overestimate. It's really close to my curves that I have here, depending on how steep your curve is. But concave up is always going to be an overestimate. A concave down will always be an underestimate. Okay. Reason I say that and how to help you kind of think through what they're asking you when they ask you that question is we see that on this next question. Again, we don't have a picture to look at, but it's giving us an integral from 0 to pi of sine of x dx. Let's just take it one question at a time. So question A first says use the trapezoidal rule with n equals 4, so 4 equal trapezoids, to approximate the value of this integral. So one of the things we want to think about is, okay, if I'm breaking up the interval by 4, what does that mean my height is, and then what does that mean I'm evaluating each of those steps of the function at? So let's start with that, height. Okay, height, again, I can do this by saying top of my interval minus bottom of my interval divided by how many trapezoids I want is the formula behind it, but that's also worth thinking about how long do I have and how many am I slicing it into. And it ends up that we are going to be evaluating this function at every pi over 4. That's going to be the height of my trapezoids. Okay? Questions on that? So putting this into our trap formula, that says take your height divided by 2, and I'm going to show it that way, but pi over 4 divided by 2 would be pi over 8, right? Times, and then we do the first, we evaluate at the bottom of our interval first, just one time. So this would be, this number right here is just sine of 0, right? What is the sine of 0? 0. Now, if you don't remember that on this particular problem, I would say this is probably a calculator problem that we can go to our calculator and go type in sine of 0, as long as our calculator is in what mode? Radians, okay? So with that being said, I don't necessarily have to remember my unit circle values on this. I'm going to go ahead and just type it in, or just write it in here then. So if I'm supposed to have a height of pi over 4, that means we're going to evaluate this each time just pi over 4 more to the right. So my next one would be over at sine of pi over 4, which my unit circle is square root of 2 over 2, right? Plus 2 times move over another pi over 4. If I'm at pi over 4 and I move over another pi over 4, what am I at now? Pi over 2. Which sine of pi over 2 is 1. And move over another pi over 4. So this was 2 over 4. So our next one would be 3 pi over 4. Which is also square root of 2 over 2. Plus, and then our last one, which I'm going to run out of room for, so I'll put a little arrow here. We only get one of them because it's our last base. It's only on one trapezoid, and that is sine evaluated at that top part of our interval, sine of pi. And sine of pi is 0. Well, you guys are typing that in and getting me a decimal approximate here. Our decimal approximate should be whatever. Let's see, this would be that is. Agreed? Agreed? What'd you get? 1.96. Questions so far? Okay. Part B, use the concavity of the function to predict whether the approximation is an over or an underestimate, which means we kind of got to remember what that function looks like. Now, if we have a calculator, we really could just type it in and look at the picture, right? Reminder, my suggestion is always that we only set our window to that interval. So only looking at the sine function from 0 to pi. So if I were to think about what that looks like now, if you remember how to graph sine, it starts at 0, 0, goes over to pi over 2, up to 1, over to pi, back to 0. That's the first half of your sine curve, isn't it? But that's all we were asked to look at. So it is concave up or concave down? Down, right? Concave down. And if it's concave down, is it an over or an underestimate? Underestimate. So on part B, we would say that that is an underestimate. Okay. And then part C, find the integral's exact value. If it says exact value, that means we are typing that into our calculator. The integral from 0 to pi of sine of x dx. Make sure we are in radians. I'm going to do my math 9 here. Actually, I don't even think it's approximately. Okay. Does that make sense? We said our estimate was an underestimate. Our estimate is just under 2. So all seems to go together here. Any questions? Okay, now, quick sidebar here. What if I were to change this, and I know it's just your calculators before you answer this. What if I changed it instead of from 0 to pi, from 0 to 2 pi? What would it be? 0. It would be 0, wouldn't it? Why do we know that? Because sine is symmetrical. And the other part of that from pi to 2 pi is below our x-axis, right? So all of that would have canceled out what was from 0 to pi. So just kind of thinking through things. This is the first part of your assignment. It's going to be on page 316, 1 through 8. And then we'll jump to day 2. Like I said, we're going to do both days today because of our snow day. Do you need to run to the bathroom? Okay, got that down? We're going to jump to day 2 here. It is not much different, very similar to what we did with rectangles. The first day we looked at graphs. We drew in rectangles. We calculated area using the pictures and our area formulas, and then we moved on to, okay, how does that work when we're given a table of data? So we're going to do the same thing with our trapezoids. On this one, an observer measures the outside temperature every hour from noon until midnight. They record the temperature in the following table. I want to clarify this table real quick because it has N and M listed in there, and that's just so we don't confuse if they had put 12 for noon and 12 for midnight. They didn't use military time here. But that's where we start at noon, and then 1 o'clock, 2 o'clock, 3 o'clock. Those are the temperatures they give us. And I also want to kind of reword this because if we're going to do a trapezoidal approximation, it's going to say that in the question. So we're going to use a trapezoidal approximation to find the average temperature for the 12-hour period, since we are in our trapezoid section here. Okay, so what is the average temperature for the 12-hour period using a trapezoidal approximation here? So first of all, thinking through doing a trapezoidal approximation, we're going to practice that formula for trap, that we would need to identify the height of each of our trapezoids. But what is the height of each of our trapezoids? 1, right? We've got a 12-hour interval, and we're breaking it into 12, so our height is going to be 1. So as we set up our trapezoidal rule, it'd be 1 over 2, our height over 2, times, and then in the table, we just have less work. We just have to actually just put it in there, right? We use the first one once, because that would be our first base. And then every one after that, we're going to use 2 until we get to the last one. So 2 times 65, 2 times 66, 2 times 68, 70. And then I get to the last one, and I don't do 2 times 55. We just do 55, because it is only used in one of those trapezoids. Okay. Now, what I have written up there in red, the number you get if you were to type that in, what is that number? Big, yes. It's going to be a big number. What is that representing? Area under the curve, which specific to this problem is what? Not the average temperature. That's like the total temperature, whatever that is. But I don't even know what that is as a thing. But it's the total temperature, right? It's all of those temperatures just added up. So that's not our average temperature. Remember that if we want the average of a function, yeah, we need to do that 1 over b minus a times the integral. Now this is what we're doing, 1 over b minus a times the integral from a to b of our function t of t dt, okay? This part of it we are approximating using trapezoids. This part of it we haven't done yet, so let's go ahead and put that up here. 1 over b minus a. Now remember, b minus a just represents the length of the integral, and our integral is 12, right? Interval is 12. I shouldn't say integral. Interval is 12. So we need then 1/12 of our answer, or to divide our answer by 12. 12-hour period. Questions on that? In the interest of time, I will let you guys continue to type that in, put an answer on your notes, as long as you're understanding what's going on up there. We're going to move on to our second to last here. Good. Anyone still need this page? Okay, so this was in a table. We've seen it given a function, and then looking at our trapezoidal rule given a picture and understanding how we kind of apply that to here. It says, in this example, a surveyor wants to find the total area of a lake. That's your lake, okay? He takes measurements using GPS every 100 yards, estimates the total area using trap. So again, if they want us to use a trapezoidal approximation, they will say that, use trapezoidal approximation, trap. They told us that the distance between where these GPS measurements are happening is 100. What does 100 represent in this whole thing? The height of our trapezoids, isn't it? Our trapezoids are connecting those points at the end. Now the trapezoids on the very ends look really weird, so that's why I kind of went in the middle there. But there's your trapezoids happening, okay? And again, once we get that figured out, setting up trap is no different. Or height over 2. Our height is 100 over 2. Our first GPS distance, and that's what's, again, a little bit weird about this one, is 0. Okay? And so the 0 is just in there one time. Every other base or measurement will be used twice until we get to the very last measurement, which will, again, only be used one time in there. So difference from what we did on the last page to this page, this one is asking us for the total area. Setting up trap is the total area of that lake. On the last page, we were asked for the average of a function, and so we had to put in front of it the 1 over b minus a, or the 1 over our interval length, to get the average of that. Okay. Before we see our very last thing today, any questions on trap or your trapezoidal approximation? Yes. Okay, so in a trapezoid, the area formula, it doesn't matter the angle of the legs of the trapezoid. Yeah. So the fact that our one leg is not a horizontal line doesn't matter. because the area formula takes into account is just base 1 and base 2, and the height is all that matters. The fact that the legs, yeah, the trapezoids that we were seeing earlier are that as well. One of the sides just happens to be a horizontal line. It's like the difference between a trapezoid that looks like this versus a trapezoid that looks like this. They have the same area formula. This is the one we were seeing earlier. This is the one you're seeing in this picture. But it's the same area formula. And what adjusts for the fact that this one seems to go longer is that this base is longer. So, all right, the last way of approximating area under a curve that we are introduced to, and again, these are all approximations for an area under a curve, is what is called your Simpson's rule. This shows up incredibly rarely. I would put this somewhere in my notes and revisit it like the day before I take the AP exam. But the Simpson's rule uses parabolas, so parabolic shapes under your curve to approximate area. Deriving this formula is definitely not worth our time, but if we were to look at something similar to what we had before, what it's doing is putting in parabolas under our curve to find the area. There's your Simpson's rule. Okay. The formula for Simpson's rule looks very similar to TRAP, where it takes your height, but instead it will divide it by 3. This looks also very similar. Your first and last values, where we evaluate the beginning of our interval and the end of our interval, will only be used one time. Each of the other stopping places, however, whatever our height moves us to, this is where it gets different, is that it will be an alternating multiple of 4, and then 2, and then 4, and then 2, and then 4, and then 2, and then 4, and then 2 for every interior value, starting with a 4. So it goes 4, 2, 4, 2, 4, 2 until we run out of interior points. Now, this one has a limitation. It can only be used if the number of parabolas, number of equal spaced intervals that they would ask us to do, is an even number. If they said n equals 9, can't use Simpson's rule. When would I use Simpson's rule? When the direction said to. Okay, that is the only time that you are going to use Simpson's rule. And like I said, it comes up very, very rarely, worth getting introduced to. We will probably, this about the last day, we will talk about it. Well, again, it goes back to the depends on the function. And I know that our functions that I draw in here are incredibly basic. I mean, upside down parabola. But depending on the function, could be. Okay. So using our Simpson's rule to estimate, I like this example for the fact of, again, talking about the different lengths here. But your height that we would use, take your interval 2 minus 0. Your interval has a length of 2. We are dividing it into 4 equal units here, or a height of 1/2. So our Simpson's rule approximation for the area under our curve would say 1/2 divided by 3, which would be 1/6, right? And then starting at the bottom of that interval, plugging that into our function, 0 to the 4th is 0 times 5 is 0. And then after we put the first value in there, we will multiply the next value by 4, and now start alternating 4, 2, 4, 2 as we work our way through. And our next number would come from plugging in, move over 1/2. And in this particular problem, we're going to move over 1/2 for each of our values, right? So 5 times 1/2 to the 4th, whatever that is, plus, and this time we'll say 2 times 5, move over another 1/2, so we'd be at 1 to the 4th. 2 times 5 times, move over another 1/2. Oops, I said 2. 4. Alternate. And if we move over another half, we're at the end of our interval. That would be the last of our 4 equal intervals, which means I don't multiply it by anything. I would plug 2 into that last time. So the similarities, again, we have our height, but we divide by 3. We multiply our interior points, but we alternate starting with 4, 2, 4. We ran out of interior points. We use the first and last only once. Simpson's rule. Okay, using your parabolas to approximate the area instead of rectangles or trapezoids. Questions? All right. Your assignment for the second day of this is the 316, 9, 10, 13 through 18.